Hey kids, we are back to equations of lines, right? Since Algebra 1, you've been writing equations of lines. Well, remember in Algebra 1, you had multiple forms of a line. Point slope, slope y-intercept, standard form. We kind of sort of have the same thing in 3 dimensions. We have the vector form of a line, right? Components of that, pun intended, are the position vector for a known point on the line. Parametric form of a line deals with the coordinates, right? I have the coordinates I can see the coordinates of a point on a line in it. Symmetric equation of a line, I don't know how useful that is. But right, think of like y equals mx plus b. You see the slope and the y-intercept in it, right? In point slope, you see a point and the slope in it. So kind of sort of think of that with vector and parametric form in 3D. Right? In 2D, you need a point and a slope. 3D, you need a point and a direction to get any of these forms. We're going to start with the vector form of a line. So I'm going to take a point on the line. So I have my red line and a point on it, right? And this point is going to roam along the line. The direction is a vector, and this vector v is down here at the origin, and it is parallel to the line in space that I want. So point, direction, right? Point on the line, direction. I'm sorry, this point is fixed. I said I was going to roam. This is a fixed point. This is a fixed point, and this is the direction of the line through my point. Now, here is any point. This is the point that's going to roam. Right? Fixed point, direction. And now this point could be any point on my red line. Notice that from the origin, I have a vector called r sub 0. R sub 0 goes to, from the origin, out in space to p sub 0. Vector r is going to change, right? Vector r is going to change because vector r goes to this point that roams along this line. R for roam around this line. Right? But the direction of my vector is still this vector v. So notice that r, the vector to any point on my line, is the sum of the position vector and the direction. Can you see that? Right? Now, I still haven't really talked about where this a comes from, but do you believe this statement? Vector r is equal to, right, vector addition, r sub 0 plus vector a gets me vector r, right? A is my direction vector, but remember, you're like, hey, my direction vector is down there. Well, remember that since A and V are parallel, right? Do you see what happened there? Watch what goes up from V. Whee! A and V are parallel, so you can multiply A by a scalar t such that A is equal to TV, right? So I can take my direction vector, right, or the vector A that I want, multiply it by a scalar, and it'll be vector V, right? That's what that parallel vectors. Now I'm going to substitute into the equation RO plus A, and I'm going to get R sub O plus TV. Right? Vector A is equal to a scalar t times V. And that's how I get this vector A. So finally, writing the components. The components of R sub 0 are x sub 0, y sub 0, z sub 0. And the components of V, remember, V we defined to be A, B, C, right? That was this vector. And then we've multiplied it by T. That's the vector form of a line, right? Kind of think of it as point plus direction. The parametric form of a line, I'm going to start with the vector form that I had. Right? And I'm going to write R. Remember, R, the vector R went to any point on the line, x, y, z. So I substituted in for R. R was the vector that went to any point on the line. So R is equal to the fixed point and direction. And then I distributed the T in. So I have TA, TB, TC. And then I combined like components. So the horizontal component, the vertical component, and the Z component, combine like terms, kind of, sort of. And then just separated it out. Across this equal sign, X, Y, and Z. And there is the parametric form of a line. Symmetric equation of a line starts with the parametric form that we got. Solve each one of those equations for T. Right, so up here, right, get T by itself by subtracting x sub 0 and dividing by A, subtract y sub 0 and divide by B, subtract z sub 0 and divide by C, and you get 3 equations equal to T. But since each one of those equations is equal to T, they have to be equal to each other. There is the symmetric form of a line. I don't know why there's a random period there. Let me do an example here. If a line passes through these 2 points, write the equation in all 3 forms. Okay, so let's start with the vector form. Well, vector form, I need a vector. Right, and I need a vector from the origin. So we're going to use our, right, something from the very beginning. I'm going to write vector V. Vector V is going to be, right, 2, Right? 2 minus 1, -1 minus 4, and 3 minus -3. Now this is the vector, right, that kind of goes from the origin. So now I need to kind of think of this as my direction. And now I need a point. Well, I've got 2 points. So just like point slope of a line, it doesn't matter the point that I pick. And now the vector form of a line point, direction. Done and done. To write the parametric form, right, I just kind of need to break up the pieces and say, well, what is the x component? The x component is going to be 2 plus 1t. The y component is -1 plus -5t. And the z component is 3 plus 6t. There's the parametric form. And then finally the symmetric form. The symmetric form is getting t by itself in each of one of these and then setting them equal to one another. So here, t is equal to x minus 2 over 1, right? T is equal to, and t is equal to, so since they're all equal to the same t, no, I don't have to put that one. Vector form, parametric form, and symmetric form. All right, that's it for this content video. See you next time.